All right, so we have kind of leveled off numbers wise, so let's get rolling here. I'm just going to do a quick introduction for SC4D, SC4Grads, and then our speaker today. So thank you everyone for being here, and we can get rolling. All right, so SC4D stands for Subduction Zones in 4 Dimensions. It's a community-driven initiative for long-term interdisciplinary research program to understand the limits and possibilities of predicting subduction zone hazards. The group works together to create multifaceted infrastructure and other resources needed to enable new discoveries. SC4D brings together a diverse community of US-based and international scientists from a wide range of disciplines and backgrounds who study earthquakes, volcanic eruptions, and surface processes. And I'm going to drop a link in the chat here. So if you would like to join the mailing list for SC4D, you can do that. And I'm also going to drop a link for the SC4Grads mailing list, which I will introduce next to you. All right, so that is the SC4Grads one. If one of my co-panelists could drop in the SC4D link, that would be great. All right, and then for SC4Grads. Cool, so SC4Grads is a collaborative, interdisciplinary, and intercultural network for graduate students and research graduates studying subduction zone hazards. We are under the umbrella of SC4D and part of the Building Equity and Capacity within the Geosciences, the BECG initiative group. Our community is composed of graduate students, postdocs, and non-faculty researchers less than 5 years from their terminal degree from different disciplines and backgrounds. And so that is kind of our group that's hosting the webinar today. If you would like to join our mailing list, please do so. Or if you have questions, feel free to reach out to any of us who are the panelists here. All right, so introducing our speaker today, we have Rebecca de Graffenried. She is a postdoc at Arizona State University, and she will be presenting a talk titled What to Expect When You're Expecting a Lava Flow, an overview of lava flow models. Her research interests include magma degassing, diffusion modeling, and lava rheology. She has authored 6 papers and got her PhD from the University of Hawaii, and she's also done a postdoc at Bochum in Germany. And Rebecca will be starting as an assistant professor at the University of Missouri in spring 2024. So please help me in welcoming Rebecca, and the floor is yours.
Great, thank you so much. I really appreciate the opportunity to give this talk today. Apologies if there's a lot of noise in my background. I live near the airport, and it is one of the prime times for flights to be landing here in Phoenix. So if you hear a lot of noise in my background, sorry about that. So I'll start by sharing my screen and moving over to presenter mode. Okay, so as Michael said, today's talk is going to be focusing on lava flow models. This is going to be sort of the basics of what's going on with lava flows and lava flow rheology. And we'll focus mostly on 1D models. I can give references to higher dimensional models if people are interested, but we'll see how it works with 1D models. So why study lava flows? Lava flows are hazardous, but the hazards that they present are quite different depending on how fast the lava flow itself is moving. So on the left here is an image from one of the first few days of the 2018 eruption of Kilauea. And in this instance, fissures were erupting and opening in people's backyards, but the lava flows themselves were actually moving very slowly, so there was no casualties associated with this. On the right, however, you see lava flow fields from Nyiragongo, and this is a volcano whose lava flows have regularly killed people because these lava flows are very fluid and move very quickly, and it's hard to get out of the way of these flows. So we'll look at some of these contrasting behaviors, and hopefully this highlights why it's important for us to understand where are lava flows going, how fast will they move, and also what is the full extent that the lava flow will reach. These are some of the critical questions that have to be answered during eruptive crises in order to accurately give evacuation orders to try to minimize the human impacts. Unfortunately, what typically gets impacted during lava flows is infrastructure, and there's not a lot that we can do about that. You can see on the left photo that there are some homes that are going to get consumed by that lava flow. So just a quick roadmap for where this talk is going to go. I'm going to start out by introducing what is rheology and what are some of the important parameters specifically for lava flows. There are other parameters if you deal a lot with mantle rheology. There will be a lot of parameters that I don't get into for lava flows because they don't matter as much. And then we'll look at some of the different kinds of lava flow models, and then how does that relate to eruption crises. I also have an example of a code that Tom Shea mostly wrote, but I've helped with writing as well, that kind of shows what goes into coding some of these models. So what is rheology? When I say this word rheology, what does it mean? It is the study of the deformation and flow of matter. In this case, deformation and flow of lava is what we're going to be talking about. And lava is a complex material. It is not just a pure liquid. You can get some lavas that are close to pure liquid, but they will have crystals and bubbles in them as well. Lavas will form crust as they cool. So all of these different parameters are going to come into play and make it a very complicated system to try to define and model. So we're going to look at this plot first to understand some of the main rheological parameters that we think about with lava flows. So on the x-axis, we have strain rate, and on the y-axis, we have shear stress. So essentially, this plot is showing how a material will deform when a stress is applied. We'll start with what most people are probably familiar with, which are Newtonian fluids, which if you see, makes this nice line here. Slope is constant. And if you know the units for viscosity, Pascal seconds, you can probably guess that the slope of this line is the viscosity of a material. So a Newtonian fluid will always deform at the same rate, no matter how much stress is applied. Lavas, on the other hand, tend to show a shear thinning behavior. So depending on how much you stress it, you will get a differing strain rate. So it will deform at different rates depending on how you stress it. And you'll see that the slope of this line is different depending on where you sit on this curve. A lot of models will treat lava flows as a Newtonian fluid, just to make it simpler, but there are ways to incorporate this shear thinning behavior into your lava flow model. Another important property is this thing called the yield stress. This is essentially an amount of force that must be applied to a fluid in order to get it to move. Without overcoming this force, that fluid will not move. So an example of this would be mayonnaise, right? You can plop a blob of mayonnaise down and it will more or less just stay where it is, unless you put a whole lot of it on there and then it'll start to deform under its own weight. But if you just have a nice little blob there, it's not going to go anywhere. It's going to just sit there. But if you would take a knife to it, say, and spread it, it will deform and flow. So that's an example of what we would call a Bingham fluid. You can also incorporate shear thinning behavior into a Bingham fluid. So there's all sorts of complications that can happen just with something as simple as viscosity. Now, what are the things that can influence these parameters? So viscosity is influenced by a whole host of things. You have temperature, magma composition. Specifically, when we talk about magma composition, the big thing is what is the SiO2 content of that magma. So higher silica magmas will form these long polymer chains, and the polymerization of the magma is what matters in making it more or less viscous. And also the amount of alkalis that are in there. So alkalis will break up those polymers. So having a higher alkali magma will make it be more fluid because it's breaking up those silica polymers. And the same thing with volatile content. Water is also something that breaks up those silica polymers. And so that's also why higher water magmas tend to be less viscous. The example of the Nyiragongo lava flows, those actually have a lot of alkalis in them, which is why those lavas tend to move so fast. It's because they're very fluid. The crystal content is also a really big parameter that influences viscosity, and I'll go over that in a bit more detail in a later slide. And one thing that is big is the vesicle content, but I'm going to say right now, I'm not going to get into vesicles. Vesicles are complicated, and we don't have a really good handle on how vesicles influence viscosity. And if you're interested in it, Janine Birnbaum has some really cool analog experiments that were just published, I think like a month or two ago, where they did analog experiments in an MRI to look at how bubbles were influencing viscosity. And so it's a really cool study. If you're interested, you should look at it. Yield stress. We don't understand as much about yield stress in lavas, but we know that temperature, magma composition, and crystal content also influence this particular parameter. So just to quickly look at this influence of composition and temperature on viscosity, on the x-axis, we have lava temperature. On the y-axis, we have viscosity, and this is all in orders of magnitude. So looking at different magma compositions, we can see it's a little bit difficult because not all magma compositions span the whole temperature range. But if we look at things that have similar temperatures, you can see that rhyolites have big viscosities. They're like 10 to the 10 Pascal seconds. Compare that with basalts, which tend to be like 10 to the 2 Pascal seconds. So basaltic lava flows are much more fluid than rhyolitic lava flows, especially dacitic and andesitic. The photo that I have from the flyer is sitting in the middle of like a basaltic andesite lava flow. And from Mount Shasta, you'll saw that was like quite blocky. So that was already a pretty viscous lava flow. It's not moving particularly quickly like that. We look at the influence of water content. So again, these are at different temperatures and different compositions, but broadly speaking, we can see that rhyolites have more of an effect from water just because they have more of those polymers that can be broken up by the water, helping to depolarize the melt. So you get more of an effect from water in rhyolites than, say, in basalts, where it's not even half an order of magnitude difference versus rhyolites, where you can get 2 orders of magnitude difference in viscosity just purely from a couple weight percent water. That has a lot of implications for conduit flow during eruptions, but not so much for lava flows. Once lava flows are erupted, they're usually pretty degassed, looking at less than half a weight percent water, but you can get approximately, half an order of magnitude of difference in viscosity during a rhyolitic lava flow as it degasses on the surface. Now let's look at crystal content. This is one of the things that's a bit more complicated, but we understand that a little bit better. And so I'll go into some of the complications here. The reason that crystals matter for viscosity, and it's similar for yield strength, is that once you get enough particles packed into a magma, usually about 20 volume percent, they start to form a touching network where the crystals themselves are actually touching each other, and that starts to form a rigid network. And much like with the silica polymers, it's much harder to deform that rigid network than it is to just say a pure melt. And so you start to see some resistance in flow. So this is the viscosity. We start out with a magma that's like 10 to the 3 Pascal seconds. But as we continue to add crystals, we can all the way up to 90%. We've ended up with a big increase by several orders of magnitude in viscosity. One of the shifts in behavior is whether or not it's kind of a loosely touching network versus a closely packed network of crystals. And as I'm sure you can figure out, if you have a closely packed network of crystals, then it's much harder to deform that. And so that's why you see kind of a sigmoidal shape here, is that there's an increase in the effect of crystals as you add more crystals to it and approach kind of the max packing function. And of course, that's different for spheres, which are on the left, versus elongate particles. So when I say spheres, it's mostly things that are equate. So things like um, olivine or quartz, those tend to be a bit more equant in shape, where one axis is generally the same size as the other. You can get a little bit of difference, but it's mostly equant. Versus something like, say, plagioclase, which likes to form elongate particles, and especially kind of microlite-shaped crystals, which tend to be a lot more elongate, acicular crystals. Those have even more of an effect on the viscosity because you actually need less of these elongate particles before they'll start to interact with each other, and they'll start to interact with each other much more strongly. So you'll see the increase in viscosity from elongate particles is actually even more pronounced than spherical particles. So when modeling these lava flows, you have to keep in mind what is the total crystallinity of these lavas, but also what are the mineral phases that are in these lavas, what are the shape of them, how are they going to influence that viscosity. But we have fairly good handle on what that impact is, so it can be accounted for in the models. Now, if we look at temperature, temperature is going to be a big player because it influences several different parameters. Lava flows are not isothermal. The temperature will change as you transport this lava flow. They cool, as you can see kind of in this background photo here. We have this red hot bit in the center of the channelized flow, but out towards the edges, it's darker and cooler. And so when these lavas cool, they will crystallize. So you're changing your crystal content. The melt viscosity is changing, right? At lower temperature, as we saw in the plot before, lower temperature means higher melt viscosity. The fraction of the crust. I'm not going to get too much into crust behavior in this talk, just purely because it is a bit more of a complicated feature to deal with, and we don't have as good of a handle on that. But you'll see the fraction of the crust on the lava is going to be a big problem to deal with, because as it gets further away, you're going to have more crust to deal with. And some of the sources of heat change in these lava flows is just purely radiation. So you have a hot magma that's hitting the air surface. It's going to radiate a lot of heat. You have a lot of conduction as well. So as the lava flow is moving over the ground, it's conducting its heat into the ground below it. We'll see what these parameters are related to in a next slide, I think. There's also convection. So as the wind is kind of sweeping over these lava flows, the wind is helping to carry away some of the heat convectively as well. But one of the heat inputs is this latent heat of crystallization. So whenever these lavas crystallize, the formation of crystals actually releases some amount of heat. And so that's where you get this kind of complicated interplay where the lava can cool and start to crystallize, but then the formation of the crystals themselves actually helps buffer the internal temperature of the lava flow so that it stays a little bit hotter for longer. So trying to calculate heat budgets within lava flows is actually a bit of a task, but I'll go over that. So let's look at the anatomy of a lava flow and look at where some of these different heat changes are coming from. So this top part here, we have a lava flow. The melt part is this red here, and then we have kind of the cooled stuff here on the sides, which is the levees, which if you look at the background photo, kind of the dark stuff around the edges, that's what that is. There's going to be a bit of a cooled base here as well, and that's where the heat is going to be conducting away to, also into the levees. And as we can see from this kind of top view here at the bottom, the lava flow is not purely just the red hot stuff. It is also the crust that's forming on the top, which again, looking at the background photo, you can see kind of these orangey red parts of the lava flow, and then also kind of the darker bits where the crust is forming on the surface of the lava flow as well. And that's going to impact the temperature of what can actually radiate away heat. So if we look at some of these different heat changes, radiation is really important when the lava flow is first, or when the lava is first erupted and first starts flowing. At high temperature, it's going to be radiating a ton of heat. It's proportional to temperature to the fourth power. So you can imagine at high temperature, you're radiating just a ton of heat, and that's going to actually cool this lava flow off pretty quickly, which is why you see this formation of the crust on the surface of the lava flow fairly rapidly once it's been erupted. Convection is going to be proportional to the heat capacity of the air. So the more efficient the air is at absorbing heat, the more efficient it's going to be at cooling the lava flow. And then also the wind speed, the faster the wind is blowing, the more air circulation you get to help cool off the lava flow as well. Conduction, heat loss, is going to be proportional to the thermal conductivity of whatever the lava flow is flowing over. That's not going to be a particularly big source of heat loss. Heat conduction is actually a lot slower than, say, radiation or convection. You can have differences in what the lava flow is flowing over, which can influence this parameter. So say a lava flow flowing over where it's been and the ground is already kind of warmed up and hot, you're not going to be conducting as much heat. Say you have a lava flow going over a glacier, you're going to have a lot more conduction going on there because it's a cooler surface. And then the latent heat of crystallization is going to be proportional to the amount crystallized. It's not going to be able to keep up with the heat losses for very long, but it will be important for helping to buffer some of these, some of the loss of heat. So you can see in this example of the lava flow here, these little circles here are bubbles. There are bubbles present, but like I said, we're not going to get into the influence of those. And then you have your different types of crystals. So say you have your little black oxides, your little green olivines, and then your elongate plagioclase crystals, for example, of a basalt. So all of these things are going to be playing together in terms of the viscosity as well as the heat loss. And so all of these things you have to take into account when you're dealing with lava flows. So if we look at the types of lava flow models, there are a couple of types that I'm going to go over. There are more. This is just going to be kind of what is typically used, especially in terms of crisis management. So there's kind of the path-defining lava flow models, which we can predict, which allows us to forecast where a lava is going to go. There's the thermal rheological models that take into account a lot of these other rheological parameters and temperature changes that I've been going over as well. But a lot of the models actually combine the two because it's useful to know where is this lava flow likely to go, how fast is it going to travel that path, what is the maximum runout length that that lava flow can have. And then all of these, of course, can be in 1, 2, or 3D. I'm going to go over 1D implementations just to keep things simple for right now. So when we look at path-defining models, how do those work? Well, what you need is some sort of digital elevation model of a sufficient resolution, right? It's not very helpful if your pixel size of your DEM is like 100 meters. There's a lot of different topography that you'll miss out on. You also have to assume some kind of vent location, and you also have to have a way to deal with changing topography, right? Lava flows don't just leave the area they've entered. They're going to leave behind some amount of topography. And so a lot of these models will have different ways to deal with that because you also don't want the lava flow going back where it came from. That really doesn't happen in nature unless something weird has happened. And mostly what this helps produce is some sort of probability of lava flow inundation in a given area. So the way that this works is, let's say we have a lava flow that starts in the center pixel here. The codes will often look at what is the elevation in all of these neighboring pixels, and lava behaves like a fluid and will follow the path of steepest descent. So then it looks for the next pixel where what is the biggest change in topography. And then it'll send the lava flow that way, and then you shift your reference frame, look around again, try to find where's the path of steepest descent. And then it does that until whatever predefined length you want to let it run out. And there's different ways that you can handle topography. You could, some of the models will add some amount of height to wherever the lava has been so that the lava flow can't flow back. Some of height the lava is. So there's a couple of different ways that people handle it. So what's an example of this type of model? Downflow is probably the most widely used. This is a 1D model. And what you can see is you can run this model many, many times. So this figure here is showing an example of what it looks like if you run the model 200, 2,000, 10,000, 20,000 times. And assuming this is an example from Mount Etna, so they used a vent location that previous eruption had, and the yellow outline in the background here is the extent of the real lava flow. And as they add more and more runs of this, you can see the probability of lava inundation really starts to show where the lava flow actually went. You get a few extra branches where the lava flow didn't actually go. But this model is really great because you can run it very fast, right? It takes, we'll see when I do an example of the code, but it takes no time at all to run this type of thing. And so you can run it many, many, many times and get some sort of probabilistic information about what areas can be inundated by lava given a certain vent location. You will notice that this does not have any information in it about the rheological parameters of the lava, however. So this just assumes if the lava can flow as long as it wants, where is it going to go? So how is this used in terms of hazards? Well, here's a nice study for Piton de la Fournaise done by Chabrol et al., where they used probabilistic maps of vent locations and then also combined that with probabilistic flow maps from the downflow code to then produce this lovely map that shows the probability of lava flow invasion given a new eruption starts. So these probabilities include also vent location, but then also where is the lava going to go once the lava actually starts to erupt. So this is something that you can produce very easily with this downflow code. Now we look at the thermal rheological model, so that's like starting to incorporate all of these complications about what is the state of the lava itself, what is its composition, what is its crystal content, what does that crystal cargo look like in terms of shape and size. You have to incorporate heat transfer, so you have to know parameters like what is the conduction of the material that it's going over, what are some of these radiation parameters. So there are ways to get those parameters, but it's a lot of information that you have to feed into the code. However, it is very powerful in terms of producing the details of how the lava flow moves through time. And it also can give you estimations of flow length and advance rate because now you're actually interested in what is the amount of material being moved and how is that material moving. Just really quickly, one of the parameters that's really important for these thermal rheological models that I haven't mentioned yet, effusion rate. So effusion rate is the rate at which lava is erupted onto the surface. It's one of these really critical parameters, but it's also somewhat difficult to get it in real time. So this is a study by Bonnie and Wright in 2017. This Waj type curve is the one that's used a lot, but they did a nice study using satellite data to look at some of these other different types of effusion rate patterns that had been observed in Icelandic eruptions. And what you see is that there's a lot of different patterns that effusion rate can take. And you can imagine that it is somewhat difficult to actually define these effusion rate curves accurately through time in an eruption. It's a difficult thing to actually measure. So being able to actually sit there at the vent and measure how much lava is coming out, how do you do that? There's new methods now that are being using unoccupied aircraft vehicles to actually sit there at the vent and measure it, so it's not quite as hazardous for humans, because that's one of the big things is you can actually be very close to the vent without having some sort of hazard to yourself. People can also use changes in volume through time in the lava flow field itself to estimate this, but that gets very complicated because lava flows are not a uniform thickness. And even through time, lava flows may not start to extend laterally, but they might start to extend vertically. So lava flows tend to inflate through time. Once the lava can no longer break through the crust, it'll inflate instead. And so it gets a little bit more difficult to estimate volumes from that. You can also estimate effusion rate using satellite data from thermal images, which is what Bonnie and Wright did. But that you have to hope that the satellite is not obscured by clouds. You have to hope that the pixel size is actually good enough for what you want to do. So there's trade-offs in no matter what method you do. But as you can imagine, lava flow behavior is going to be very different if you have just this really sharp peak in effusion rate and then it peters off, versus if the effusion rate peaks, goes down, peaks again, and comes back down, you're going to change the way the lava flow behaves. And this double pulse type is very similar to what was happening in the Kilauea 2018 eruption, because the first phase of the eruption started lots of fissures erupting. You've got a lot of material being erupted, but then it started to wane a little bit. But then a new pulse of magma hit the system, and all of a sudden you saw a big spike in effusion rate across the system. And that caused some of the lava flows that had actually stalled out to then reactivate. And it also reactivated some of the old fissures. So understanding how effusion rate changes through time is pretty important for these thermal rheological models. Okay, after that somewhat sidebar, one of the really popular thermal rheological models is FlowGo. So on the left here, we have kind of the workflow for how this works, just to give you an idea of how complicated it is. So you have to have a bunch of your starting parameters, and then as you step through the model through time, you have to, at each step, you have to figure out what is the heat loss for this particular time step, and then calculate your cooling rate, and then how much crystallization occurs for that, and then what is your new crystal content. And once you have all these new parameters, what is your new viscosity and yield strength? And then once you have that, you can calculate how fast it's moving at that time step, and then get your new state, and then figure out, is your lava flow going to keep moving? Does it have the necessary parameters to keep moving? If it does, then you go back through and you advance it however far it's going to go based on what you just calculated. And then you do the whole loop of calculations again until the lava flow is no longer moving. So what you get out of that is, here's an example from some of the Mauna Loa flows. And it shows as the lava flow is moving various distances from the vent, you can calculate how fast is it moving, and you'll see near the vent, it's moving quite fast. And then that kind of peters off pretty quickly as it cools and it's not moving very fast. And channel width, so as this lava flow starts to cool and slow down, it's actually going to spread out laterally, which is what we saw in the Kilauea 2018 eruption for some of those later flows that made really big, flat, wide lava deltas. And then temperature, just to show what the temperature looks like as it changes over distance. I'm not sure if these axes are correct because that shows it's getting hotter. Yeah, I'm not sure what that is there. But the lava flow does cool in sort of like this exponential decay fashion. So what can we create with that? Well, here's another lava flow hazard map for Mount Etna. And what you'll see here is now these colors are tied to effusion rate, because the effusion rate is going to change how far this lava flow is going to be able to travel. And I will say in this particular instance, they did use a combination with downflow to get where the lava flows themselves are going to go. But one of the things that you can get with FlowGo that you can't with downflow is how far is this lava flow actually going to go given some amount of effusion. So these are very powerful tools, and they run very fast because they are 1D models. So you can run a whole lot of these models without it taking a lot of time. to produce good probabilistic estimates of where lava flows are going to go, how fast they're going to move, and how far they're going to go. So just to show an example of what that looks like for a code, here's a code that we have in it. And so that's the Puna DEM. So we have our DEM here, and then we will calculate the change in that. And then once it calculates the flow path, then we run the actual flow model. And the flow model will call all of the data that we produce for the flow path here. And so I'm not going to go over each individual parameter. It's going to take all of the things that go into it. So assumptions about the channel of the lava, or the channel that the lava is flowing through, looking at the density of the lava. We have to input a composition, an eruption temperature. We have to assume stuff about the thermal state of the lava, what's happening during radiation, what's happening during conduction, what's happening during convection. Looking at the crystal content. What is the starting crystal content? How does the crystal content change with changes in temperature? What is the latent heat of crystallization? And then we do all of our calculations. So then we have to give it kind of the initial state of the viscosity, the yield strength, what is the thermal parameters. And then we have our whole loop where we have to calculate everything. So just what I showed in the kind of the flow chart for FlowGo, it's exactly this, but actually the calculations are done. So calculating our heat loss, our degrees of cooling. But one of the things that we built in here is that if the lava does not have the power to keep moving, then the code will stop. And then we'll plot a bunch of stuff. Let me just make sure I have the correct. Yes, so this will be for a basalt. So we just run the code. Always a surprise to see if it works. Was working yesterday. Yep, there we go. So here is our DEM. I'll make it bigger. It's a little bit harder to tell, but there isn't a whole lot of relief on this part of the island, so it's not going to show up a lot. But this is kind of the area of the 2018 eruption. So I'm going to select a vent point and very carefully double click. And so you'll see the lava flow is now following its path of steepest descent. And it's doing its calculations. And so if we look at the results here, so what you can see here is this lava flow is moving for quite a distance. It was like 15 kilometers or something like that. So what you see is where these values start to go vertical, that's where the lava flow stops moving. So as the crystal content starts to ramp up, the yield strength is starting to go asymptotically to infinity. The viscosity is also starting to go asymptotically to infinity. Our lava flow doesn't cool very much. It's maybe about 50 degrees Celsius over the course of the whole lava flow, so it's pretty well insulated. The velocity generally follows a trend. It's a little bit unstable. But then also the channel width. So once this lava flow starts to slow down, again, that channel width gets much larger. And then if you're just interested in what are the relative proportions of the different heat losses, radiation is of course going to be the major heat loss. And then also with forced convection and then conduction. And then also calculating what is the crust fraction of the lava flow. But you see that took essentially no time at all for this code to run. So you could even automate it better than that so that you don't have to click where the lava vent is. You can mess around with parameters very quickly. So what is the effect if we start our lava with a lot of crystals versus what if we gave a higher effusion rate of lava? What if we gave a lower effusion rate of lava? Since we started a little bit late, I won't do examples with different compositions. But you can very easily input different compositions. I have an andesite and a rhyolite as well. So these types of codes are very useful for doing fast calculations and trying to figure out where is the lava flow going to go, how far is it going to go, how fast is it going to be moving to those different positions. So then to go back here. So some of the advantages and trade-offs here, if you have higher dimensional models, so like a 2D and 3D model, you can get a lot better accuracy in what is happening, but your runtime is much longer and you have to kind of have access to a computing cluster in order to actually run these models with any sort of helpful time frame. You can get a lot of model runs done if you account for just slope. And you can get really good probabilistic maps out of that are very useful before a crisis or in the early stages of a crisis when you're trying to figure out who's likely to be threatened by lava flows. But they're not as helpful for determining the advance rate and the runout distance because you don't usually have a lot of rheological data built into those. The thermorheological models can calculate the advance rate and the runout distance, but as you saw, there's a lot of assumptions, parameters. You have to have a lot of knowledge of what's going on in the lava flow itself in order for these models to actually give good answers. You can take like Monte Carlo approaches to this to try to get around this particular problem. But again, now you're increasing the number of runs you have to do. So sticking to 1D models probably helps a lot with that. The other thing is that eruptions are dynamic. That I keep going back to the 2018 eruption because that's the one that I'm most familiar with. But there was a lot that was changing on a day-to-day scale with those eruptions. We had different vents opening, different amounts of lava coming out of the different vents. And so having to run multiple models for all of these different lava flows that were going on. So these more simple models help a lot in terms of all of that. But now that the crisis is done, a lot of the higher dimensional models to really understand more about the lava flow science itself, that's where this comes in. And it's a lot more helpful in that instance, using these higher dimensional models that are a little bit more accurate. So I will go ahead and stop there and take any questions that people might have.
Thank you, Rebecca. That was a fantastic talk. If you have a question, please post it in the Q&A section at the bottom of the screen, or feel free to raise your hand. As we're waiting for questions, I have one for you. With kind of looking at bubble viscosity, how does that change where you are in the flow, like kind of compared to the top or the bottom of the flow? I'm thinking about how it's moving.
Yeah, so that's also bubble distribution is quite different. So I'm going to go back to the 2018 eruption. So one of the later flows, there was actually variations in the amount of gas in the lava as it was coming out. So some of the material when it was coming out was actually very gas rich and you had a lot of bubbles. And so the bubble volume was great. But then during other parts of the eruption, the material that was coming out was very degassed and it was much more dense. So you can have variations in total bubble content just from what's coming out of the vent. But also you can have distribution of bubbles both vertically and horizontally within a flow. At least in basalts, bubbles can generally decouple from the melt. So the melt viscosity is low enough that you can get bubbles to rise through it. But smaller bubbles are just kind of trapped and carried along with the flow. As they continue to degas, you might get more bubbles further down the flow, but then also you can get where the weight of the lava, once it starts to get thicker, can start to squish them out. So it's actually, it's a very big complication in terms of what is the actual distribution of the bubbles. Also, along with what is the effect of the bubbles themselves. So bubbles are sort of the frontier of viscosity studies right now.
Cool. Thank you for that answer. That's super interesting. We've got a couple questions that have come in. The first one is from Heather Winslow, and they ask, are you able to address multiple event locations erupting at the same time in this code?
Yeah, theoretically you could. So this was just a code that we put together using the equations from FlowGo and an implementation of what downflow does. You could very easily code it to have multiple events, just because this was a code that we designed for a lava flow rheology class. So we didn't get into quite that level of complexity, but you could very easily incorporate multiple events into that and just have several parallel codes running at the same time. I'm not quite sure how it would handle if some of like the lava flows were starting to interact with each other. Not sure that it would handle that particularly well. You would probably want a higher dimensional code for that to look at the effects of 2D interactions.
Awesome. All right. And then another question from Brenna Halverson. She asks, hi, Rebecca, great talk. I have a few questions in regards to the model you showed. What viscosity model did you use with it? Was it just crystal content, and was there any shape or size component taken into consideration?
Yeah, so what I just demoed, for the melt viscosity, it's just using the Giordano et al. 2008, and then the incorporation of crystals using the Costa et al. 2009 set of equations. So it has both the melt and the crystals incorporated into that. So it's the way that that happens is that we calculate the original melt viscosity and then the relative viscosity increase from the crystals based on the Costa et al. Equation. For this one, what I showed, it's just using 0.1, yeah, the volume fraction was 0.1, so 10% crystals, assuming they're equant, but then letting them grow throughout the course of the eruption. I think it got up to like 40-ish% by the end of the flow, if I remember the plot correctly. And I think this was just assuming it was an equant shape, but it's very easy to incorporate the elongate shapes into that as well. And then I also see the channel width. So the way that the width is calculated in this is we are assuming some amount of, we have the effusion rate as a fixed value. And so the volume that is coming out has to go into something. And so it's a balance between what is the thickness of the flow versus the width. So once it's not moving very far forward at any point in time, we fix the thickness of the lava flow, so then the only thing that can change is the width. So that's why the width is changing like it is. So it's just a volume balance.
Great. Well, we don't have any other questions, but if you have one or two more that have come up, feel free to post in the Q&A section.
See, one more has come in.
Awesome.
Actually.
We just have two more. Perfect.
Oh, a couple of actually. So from Mahina, how far into an eruption can you reasonably estimate or predict changing topography? Yeah, so that's a really good question for some of these eruptions that go for a long time. And I sound like a broken record, but I'm going to go back to the 2018 Kilauea eruption, where we had that first phase of the eruption that emplaced a bunch of lava flows. And then in the second phase of the eruption, we had things that were erupting on top of old lava flows. So obviously the DEMs that were previously made for the region are no longer going to be good. They're not accounting for that new topography from the new lava. And then you also had lava flows that were running into old lava flows and then deflecting down towards the coast where maybe they might have kept going along the land. So yeah, it's it's really difficult once you get these really complex lava flow fields because you do have topography that has changed and you may not have the new topography measured. I think they were conducting LiDAR campaigns in the middle of that particular eruption. So they were looking at how the topography was changing in the middle of the eruption, and that might have helped. but I don't remember exactly when the LiDAR campaign happened, but that might be something that can happen if it's like going to be a really big problem. Some of these more rapid methods can be used to capture what is the new topography, and then you can incorporate that into new models. Yeah, so looking at this next question, I think early on you said that most magma degassing happens prior to the eruption. With that in mind, for those of us who study subduction, how much can the study of volatile interaction and metasomatism in the subducting slab inform arc volcano hazards, or is the flow behavior mostly insensitive to behavior near the subduction interface? Yeah, I think that's an important question to ask. I think it really depends on the magma composition and how volatile rich the magma itself is. So yes, a lot of lava flows come out mostly degassed, but that's relative to water and I guess CO2 and sulfur as well. But we don't really know how some of these other volatiles play into viscosity as well. I'm not sure about CO2 and sulfur and viscosity at all. Really, it's mostly water that people have studied. So I think understanding what the volatile budget of some of these other volatiles is actually going to be really important for understanding lava flows there. So like Kilauea is an example of just an ocean island hotspot volcano. The amount of volatiles available there are pretty low anyway. But if you get lavas that manage to retain their volatiles as they come towards the surface, they can be a lot more fluid. So like rhyolites may not fully degas as they rise towards the surface just because they have a lot of water and they have really high viscosities. Bubbles can't escape as easily from them. And so you might have a little bit more water in the actual matrix glass, or I guess matrix melt still at that point, that can help the flow to move. But that's going to be very different for basalt, where bubbles can actually decouple during ascent. Hopefully that helped to answer your question. I think it's just generally knowing what is the volatile budget of the stuff that's erupting, what is the composition of the stuff that's erupting. Those are really big questions for subduction zones.
Great. Well, that looks like we have one more question that came in. Oh, it's just a thank you from Jeremy here.
Yeah.
All right, Rebecca, well, thank you so much for your talk today. It was super interesting and we appreciate your time. And if we could all thank Rebecca again, that would be great. I posted 2 links in the chat. They are 2 surveys, one for SZ4Grads and SZ4D about the event, so how we can kind of improve and what we've learned over time here. As well as we'll have a different link for the webinar next week, so look out for that one. There'll be an automatic registration that we're going to be switching to. And that is all that we have for you guys today. Thank you again for attending, and we'll hope to see you next week.
Thanks for attending, everybody.